Hello, hello, hello. So, I want to take some time to go over stuff that, a little bit more of the details of chapter 8, because we didn't do as many multiple choices as I wanted to. Got to work on that one. But this may help you. The standard error. We know that the standard error for here's for our proportion, here's for our standard deviation when we don't have sigma, and here's standard deviation when we do have sigma. Okay, next. Remember, we must have an SRS or an RS. Otherwise, n times p naught, or n is greater than or equal to 30 does not matter. You're going to have to throw out the data and restart and make sure it's a well-designed data, which includes the SRS. And of course, yes, the independence. Next, as I look at the level C, please remember the level C represents the success rate of an interval. We are 95% confident that the true mean is going to be captured within within two intervals. That is our success rate, which means that other 5%, because I'm talking about 95% in this case, is our lack of success rate, or we can call it our failure rate. Okay. Point 4. We use T star instead of Z star, of course, when we know sigma is unknown. And the whole rationale is that what we're going to be doing rather is replacing our standard deviation for that sample as an estimate to replace the sigma. But we already know that as our standard deviation for the sample goes up, or as our sample size, I should say, goes up, it starts to look more like a normal distribution anyway. Okay, but back to this point. To this point, the whole rationale behind this is that all we did was replace the sigma for the S, and then of course we're going to have a critical T value, not a critical Z. Okay, next. The T distribution is different than the normal because, first thing, the T distribution is wider and slightly different. And we're going to be looking at a problem like that on the back in a few minutes. I want to just get through all of these. We already established as the sample size increases, the T distribution becomes more like a normal distribution. Okay, more like a Z-score. Next, it has a heavy tail. And then we're going to look at our T charts and our Z charts in a minute. So, with that being said, let's look at them. Here, let me try to get both of these on the screen. Okay, so I said that the tail is heavier for the T distribution. Well, visually speaking, you see how that right there, it's not quite hitting. Not quite hitting. Right here with our Z, it is. And I know your thoughts are, well, isn't that just how they drew it? And the reality is, let's look at our T distribution, and let's look at our critical T values. And as we look at our critical T values, look at all these values inside of here. It looks like to me the lowest critical T is 0.674. I may be a little off, but it looks like that's the lowest one. Okay, but let's look up here. The highest critical T based on this is 636. Okay, so at some point it cut off, so I'm going to have to rewind. I hate when that happens, but the fact that it did. Okay, so as I was saying, here the T distributions it's wider because it's wider meaning more values, and that's because right here I see that the largest T or largest critical T is going to be 636. But now let's look at our Z distribution. Our Z distribution, we're going to look in two different ways. Look down here, and as I look down here, it goes from 0 to 3.4. And yes, we have gotten Z scores that are like 10 point something, but what happens? It's essentially 0, which means it gets so small, no one really cares. Because as the Z score increases, the probability of something being greater than that Z score gets closer and closer to 0. So as I get back to this specific point right here, look at that, look at the drawing, but more specifically, look at what the critical values are. But we don't even use that chart. We use this chart for the critical values. Somebody was nice enough to do it with our key percentages. And as we look at this, let's look at our infinities. Look at those critical values. And look here. When we have a 99.9% confidence level, we have a critical T of a critical Z of 3.291. Wow. So we're talking about with a 99.9% confidence interval, which, remember, what that looks like is basically this, and you've got, here's your interval right in here. And you know that's not drawing the scale. Okay, so that means that there's what? Less than 0.1% that is, that does not work. So you can see my drawing's not drawing the scale, but just to make a point, this is close to 100%. You almost have the total area under the curve. And the critical Z is only going to be 3.291. So we can see why. Remember, our infinity uses our Z, and we can see why, as we look here, how these tails are smaller with the Z, and going back to my original point, how they're wider or bigger with the T. Now, I want to go back and talk about this problem. Where'd it go? Slightly wider. So, as I turn to this next page, right here, I want you to take a moment and look at these two. Now compare them to what we just did. I want you to figure out which of these two is the Z, normal distribution, and which of them is the T distribution. Yes, we have a degree of freedom, but don't worry about that. Just be concerned about the idea of which shape goes with what. Go ahead and pause. Okay, welcome back. Okay, so you should have guessed, as you can see here, the dot plot is the normal distribution, and the solid one has a degree of freedom of 2. Or more specifically, and again, we're not concerning ourselves about the degree of freedom. We're concerning ourselves with how do these two curves look different. Okay, and you can see here the T distribution, remember we said it earlier, has more areas under the tail. And we looked at the numbers on why that worked a couple seconds ago. Okay, now, since we're talking about, well, let me see. Okay, as I look at this right here, below we have these graphical representations. And the question is, in this case, discuss whether normality conditions for constructing a T confidence interval. Okay, now, I'll be honest with you, the majority of the time, when it's a T interval, they rarely say it is going to be, our goal is to get to normality or to get to normal conditions. But the question is which of these would be the closest? And remember the three things we have to look at. We have to look at if there's outliers, automatically reject. Then we have to consider our sample size, and we have to consider our skewness. And the last two, the order is up to you. Okay, so take a pause, and let's see what you get. Okay, welcome back. So here are our answers. Okay, for A, it is moderately skewed, but since N is going to be 30, it's safe for us to use the T procedure. So, yeah, we're saying here, because of the idea of, yes, they're using CLT. Yes, they're using CLT with N being greater than 30. And I'll be honest, some textbooks go with 40. They really do. Okay? But we will go with what they said. Okay, since it's greater than or equal, since it's equal to 30, that T procedure is going to be okay. Now let's look at B. Don't you guys see the outliers before I even mention them? Here, it's not advisable. We did this today, didn't we? You have to check the 1.5, the outlier, okay? And here we have strong skewness. Maximum value is close to meeting that rule, which means that it seems like to me, if you did the math, it's not quite there. Okay, but it's so close that, and it's such a small sample size, they're saying no bueno, not advisable to use this procedure. And then the last one, let's see, don't see any outliers. It's strongly skewed, has no outliers, but your value for n is 45. So it's going to be safe to use the T procedure. Again, because of the idea of n is greater than or equal to 30 using CLT. So I wanted to make a point of making sure you saw those. Now let's go back to other points I want to make. Okay, so but the best way to reduce bias we already know is to increase the sample size. But if it's poorly designed or there's bias in the collection or bias in the experiment, you need to just toss it and start over. Next, please remember that the mean of all distributions are equal to 0. And what I'm saying is that when we standardize it, and as we look at our z-score here, our z-score are based on the values from 0 to 3.4, and it can go beyond that, but it's plus or minus, in which that mean, if I were to write on my sheet, which I'm not, we know the mean right there will be equal to 0, because remember the whole premise is that's how we standardize it. Meaning, how do we compare SAT scores to ACT if they're two different, one is 4-digit values and ACT is 2 digits, so how do we compare? By standardizing them, so that give them a z-score. Okay, so just remember that. That might be helpful. Okay, next point right here, your margin of, the more confident means you have a larger critical value, so your T star, your Z star here, which means you have a larger margin of error. Well, doesn't that make sense? Just look at the mathematical aspects of it. Okay, next. Here, given an interval, the point estimate is going to be the midpoint. And if you want to find the margin of error, what you need to do is take the endpoint of, and I'm going to put a little scribble here so you don't think that's a minus sign. The endpoint of the endpoint or the beginning of the interval, I would go with the endpoint, and then subtract is x bar plus or minus. I'm just going to go with T star. It's the same for Z star. And then here, your standard error. So the standard error of x. Okay, so as we look at this right here, the whole point is that if you have the interval right here, which is calculated by this, to find the point estimate, it's going to be the midpoint. You're solving for this. But if you have the intervals right here, you're just going to take that value, subtract it from whichever end you want, and that's going to, of course, give you the leftover, which is the margin of error. Last thing that I want to mention is good or okay to use the interval. I've said this before, but just reiterating. When you have no outliers, you have slightly skewed or small sample size, heavily skewed but large sample size. Remember, still no outliers, looking at CLT. And remember, that is not bueno if you didn't have your SRS or your independence that was not mentioned or understood to have occurred at the very beginning. So I hope this is helpful, and good luck. Have fun studying. Yeah, fun, Yarborough. Are you kidding me? Well, study well, study wise, and study with a partner. Have a good one, guys.